I really love the types of simple combinatorics problems that can be solved just using elementary reasoning. One of the principles that is at the heart of combinatorics is the pigeonhole principle. And it is a nice example of a principle that is very easy to apply. It can sometimes be applied in subtle ways or in tricky ways, but the actual principle itself is so incredibly easy to understand. And we can use it to answer basic questions. Take a look at the one on the board here. Suppose that there are 365 days in a year. I don't want to think about a leap year in this example. So let's suppose that there are 365 days in a year. The question is, how many people are needed to guarantee that two of these people have the same birthday? One of the ways that I like to think about combinatorics problems or counting strategies is to play devil's advocate. Like, how could we get as unlucky as possible with this problem, right? Well, maybe the first person that we look at has a birthday of January 1st, and the next person that we run into has a birthday of January 2nd. The next person's birthday is January 3rd. Suppose that you have a whole lot of people that have all different birthdays. In other words, that we cannot yet guarantee that two of them have the same birthday. How long could we go? Like, how far could we hold out before we would realize that two of these people have to have the same birthday? And remember, we could get lucky. The first two people that we pull into a room might actually have the same birthday, in which case we only needed two people. But the question here is about making a guarantee that two people have the same birthday. So to answer this question, we're going to use what is called the pigeonhole principle. And I'm going to state, first of all, a sort of simple form of this principle. So this is called the simple form. And it really is a very, very simple form. So let's write down what it says. It just says that if n plus 1 objects are placed into n boxes, if n plus 1 objects are placed into n boxes, and by the way, those boxes are really the pigeonholes, and the objects are basically the pigeons. We have n plus 1 pigeons that are going to fly into n pigeonholes. If we have that set up, then at least one box, right? At least one box contains at least two objects. At least one box would have at least two objects in it. Let me start by writing down a very simple proof of this principle, and then we'll use the pigeonhole principle to go back and solve our question at the start of this talk. The proof is generally done by way of contradiction. And the way that the contradiction goes is that you suppose, by way of contradiction, that all boxes have at most one object in them. So let's assume each box contains at most one object. So in other words, suppose that there does not exist at least one box that has at least two objects in it. Every box has at most one object in it. Well, since I have n boxes, since we have n boxes, and each box has at most one object in it, we conclude that how many objects could we have? Right? We have n boxes. Each box has at most one object in it. So how many total objects could it be? Well, we conclude that we have at most n objects. Right? But that's a contradiction because we were assuming that we had n plus 1 objects to begin with. Contrary to having n plus 1 objects in the first place. If you really stop and think about it, it's almost proving itself by common sense, right? If every box had at most 1 object in it, then you wouldn't have more than n objects. So as soon as we have n plus 1 objects, then at least 1 box has at least 2 objects. That's the proof. Feel free to pause the video if you need to stop and either write it down or think about it a little bit further. I am going to erase the proof because I want to save some space here to actually solve the question that I asked at the beginning of this video. The tricky part about the pigeonhole principle is sometimes just figuring out what are the pigeons and what are the pigeonholes. In other words, what are the objects and what are the boxes, right? In this birthday problem, right, what we have are 365 days of the year. And in fact, I'm now going to give the solution to this question. And to do that, I have to establish what are my objects and what are my boxes. Well, let's imagine it this way. Every person gets placed into a box that is labeled with their birthday, right? So what are the boxes? If the boxes are labeled with the possible birthdays, then my boxes, the boxes are the days of the year. Okay, so just to draw a little visual for this, we might have January 1st as a box, and then we might have January 2nd as a box. January 3rd is another box. Each possible day of the year has 1 box, and we go all the way to December 31st. This is going to be 365 boxes. We have 365 boxes here. And so that is n. That is n. We have n equal to 365 boxes. So according to the Pigeonhole principle, we would need 366 objects. If we're going to put each object into a box according to when their birthday is, then in theory, if we would like there to be at least 2 people with the same birthday, that's 2 people being placed in the same box, right? We would need at least 366 people. So by the Pigeonhole principle, we need 366 people to guarantee 2 people have the same birthday. It's a pretty simple application of the Pigeonhole principle. This is, after all, what I'm calling the simple form of the Pigeonhole principle. Let me take a slightly harder version of a problem involving the Pigeonhole principle. Of course, I don't want to overplay this as being super simple all the time. Even just recognizing that we have to use the Pigeonhole principle to make an argument is sometimes the key step to doing the problem. But let's take an example. Actually, before I do another example, I just want to make a quick remark about this Pigeonhole principle. It does not tell us which box will have 2 objects in it. So if I have 366 people, I can be guaranteed that 2 of them will have the same birthday, but I don't know which birthday that is. Or maybe there's even more than 1 of them. And I don't know which one or ones those are, which dates those are, where we have more than one person with the same birthday. So let me just make that as a remark. The pigeonhole principle does not identify which box receives more than one object, right? Doesn't say, pigeonhole principle doesn't say which box contains at least two objects. We can't get that much mileage out of it, but we can guarantee that there is some box, there exists a box where that is the case. Now, as a follow-up question, I want to sort of extend this birthday question just a little bit. How many people are needed to guarantee that at least 7 people have the same birthday? So now I don't just want there to be 2 people with the same birthday. I would actually like to see how many people would it take to guarantee that at least 7 of them have the same birthday. So this is kind of a more general version of the pigeonhole principle. And it can be solved, again, kind of just from common sense. But I just want to set up, again, the boxes as being, the different days of the year. So we can state this as kind of a, let me just call this an extension of the pigeonhole principle. This is sort of an extension of it, which is that we could say, let n and r be positive integers. And the question is, well, how many objects would I have to, let's leave this blank for just a second. If this many objects are distributed to n boxes. So we still have n boxes. But what I would like to do here is I would like to guarantee that at least one box has at least r objects. So instead of just 2 objects, I would like to guarantee that there's at least r objects in a particular box. Well, what I could imagine, guys, is I could imagine that every box is getting sort of equally filled up at the same rate as I put these objects into the boxes. And let's suppose that every box fails to have r objects in it. How long could that happen? How many objects could we, as devil's advocate, put into these boxes without having r objects in any box? Well, the answer is that every box could perhaps, I'm going to now fill in this line, every box could perhaps have r minus 1 objects in it. That would be n factors of r minus 1. Every box has r minus 1 objects, but for sure, by the time you put 1 additional object into a box, beyond that, now for sure there's a box that has at least r objects in it. This is just a generalization of the basic pigeonhole principle that we were talking about earlier. So in this example of this question, the solution to this question we can apply this extended form of the pigeonhole principle. Namely, we would like to guarantee that there are at least 7 people with the same birthday. So we take, again, N is 365 boxes, and R is actually 7. We would like there to be a birthday that 7 people, at least 7 people, share. And in order to guarantee that, we need to have, according to my formula, 365 times 7 minus 1 plus 1 different people in order to guarantee this. In other words, this is 365 times 6 plus 1. This is quite a good number of people that we have to have. And we can pull out our calculator really easily and figure out that this is 2,191 people in order to make that guarantee. Okay, so this is a nice application of the pigeonhole principle as well. Okay. Let me show you a couple of other applications of the pigeonhole principle that are maybe not quite as clear-cut, not quite as simple. So let's try another example. So we have the pigeonhole principle, and then we have sort of an extension of that pigeonhole principle. In a little while, I'm going to give you an even stronger form of the pigeonhole principle. So far, we're just talking about the simple form, the basic form of the principle. Let's try this example. Here we go, 100 adjacent homes. Let's say we have 100 houses that are lined up with addresses. Let's say that the addresses range from 1,000 up to 1,099. Those are the street addresses of these homes. They're all on the same street. And we just label the houses with numbers like so. On a given day, on some given day, let's suppose that 51 houses have mail. 51 out of these 100 homes have mail. What I would like to prove is that there must be 2 adjacent homes that have mail. So that there are 2 adjacent homes with mail. So it's a proof, you see. We're going to be doing a proof here, and it doesn't explicitly mention the pigeonhole principle anywhere. That's one of the challenges of the pigeonhole principle, is even recognizing that we should use it. And even after we've recognized that we should use it, there's also the question of how to set up the objects and the boxes, right? You might think that we would set up the 100 houses as the boxes. In other words, we would have 100 boxes here. But we only have 51 homes that are going to have mail. Let's suppose that we put objects, let's say that we put a pigeon in whatever house has mail. In other words, we put an object, the object being the mail, goes into the box that's labeled. I mean, you literally can imagine 100 mailboxes as if those are the 100 boxes that we have, and we're just going to literally put mail into those boxes. But the problem is that we don't have enough houses with mail. We're not going to guarantee that there are 2 adjacent homes that have mail that way, right? In fact, we're not putting 2 objects in the same box that way. So there's a trick here, guys. We cannot use each of the 100 homes as if it was a separate box. Instead, what we need to do is we need to find a way to create only 50 boxes. Because I have 51 objects. If I have more objects than boxes, then I know that one of my boxes, at least one of my boxes, has at least 2 objects in it. So what we're actually going to do here, guys, is we're not going to create 100 boxes. We are going to create 50 boxes by combining adjacent homes to each other. So in other words, what we are going to do for the solution, this is a little tricky. This is a little bit tricky. As an application of the pigeonhole principle, what I'm going to try to do here is I'm going to create one box for each adjacent pair of homes. And I think I'm going to visualize that. So I'm going to draw a box. The first adjacent pair of homes would be the homes with addresses 1000 and 1001. The next box over would pair up houses 1002 with 1003. The next box would be 1004 and 1005. So we label, right? We are labeling 2 consecutive homes to share a single box. And as you can see here, guys, there are 100 homes in total. Because I've paired them up here, we have 50 boxes. So that would be n. N is the number of boxes. Let's suppose that there's 50 boxes. And now how do we put objects into boxes? We're simply going to put an object into a box if it's male that belongs to that house. Okay. So whichever of these 51 homes has male, right? We're going to find where they are labeled here. And we're going to put the male into the box that has that house as one of the 2 labels on that box, right? So let's just say it this way. We place 51 objects, which is the male, into the boxes with the corresponding labels, address label. Okay, and by the pigeonhole principle, 2 of the boxes, 2 of the objects have to end up in the same box. So by pigeonhole principle, we have to reference this principle. This is a very important idea behind the solution. So we should definitely make a note of when we're using this pigeonhole principle, right? By the pigeonhole principle, there is at least one box with 2 objects in it, at least 2 objects, but it would be exactly 2 because we can't put 3 pieces of mail into a box that's only labeled with 2 addresses, right? So there is at least one box with 2 objects in it, meaning that both homes with that label, with that labeled box, let's say, both homes with that labeled box have mail. In other words, so there might be this box right here, might have 2 objects in it, and that just means that both home 1004 and 1005 had mail, right? So 2 adjacent homes have mail. Okay. The trick to this problem is setting up the boxes. You might wonder, well, do I have to set up the boxes that way? The answer is pretty much, if you want to solve this problem, you do need to do it this way. You might wonder, well, could I do 50 boxes some other way? Maybe I combine 1000 with 1002 and 1001 with 1003 or something like that. Maybe I don't label them with consecutive numbers, but then I won't draw the conclusion that I want to draw. I might be able to use the pigeonhole principle to say that out of the 50 boxes, there will be a box with at least 2 objects in it. But if I want that to mean that 2 adjacent homes had mail, then I need the labels on the boxes to have been set up correctly in the first place to be labeled with adjacent addresses. So it's actually quite important that we set up the boxes correctly. Let's do another example of the pigeonhole principle. So this is just using the simplest form of the pigeonhole principle. N boxes, N plus 1 objects. Putting those into those boxes, there has to be a box with at least 2 objects in it. Okay. What I want you to be thinking about as you're looking at some of these examples is I want you to start recognizing that the pigeonhole principle is really the principle behind the solution here. Okay, so that you can recognize in the future when you see a problem, you say, aha, I need to use the pigeonhole principle to solve that. Let's do another example. Here's another example. Given m integers, let's say a1, a2, a3, and so on up to am. So suppose that we have m integers here. I didn't say anything else about them, just that I have m integers. Let's show that there exist consecutive integers in this list. So let me label those. Let's say starting from AK plus 1 to AK plus 2 up to, let's say, up to A sub L. Okay, so there's a consecutive list of integers from that original list such that if I add up those integers, AK plus 1 plus AK plus 2 plus ... all the way up to A sub L, that this is divisible by m. That this number right here is divisible by m. Ooh, this is even a little bit more abstract than the previous example. Here, is the pigeonhole principle clear? Somehow that's going to be what it's about. It actually looks like a problem in number theory, showing that somewhere in this list of integers, we can add up some consecutive numbers from the list, and the result will be divisible by m. So this is kind of the trick. We're gonna do this as a proof. Notice that all of these pigeonhole principle applications are really proofs. Some of these more clever applications are proofs. And what we're going to do here is we're going to create some boxes and some objects again. Specifically, the objects that I'm going to create, you might think that my objects would just be the original numbers from the original list, but we're actually going to have to do something a little more clever here. So we're going to consider the numbers. So here they are. We're going to consider just A1. Then we're going to consider A1 plus A2. Then we're going to consider A1 plus A2 plus A3. So we're going to add up, starting from A1, a certain number of the integers in the list. And the very last sum that we would create would literally be adding up all of the m numbers. So this is a list starting from A1, A1 plus A2, A1 plus A2 plus A3, and so on, This is a list with M numbers in it. Right? You can see the number of things listed here is M. And if any of these numbers is divisible by M, then we're already done. So if any of these numbers is divisible by M, then we are done. Right? Because we're being asked to show that somewhere we can find a consecutive list of integers whose sum is divisible by M. Well, everything in this list is a list of some of the consecutive integers from my original list of numbers, right? So anything here would qualify. Anything here would be a sum of consecutive integers in the list. And if any of them was divisible by M, then we've shown what we need to show. Otherwise, this is where the more interesting part of the argument comes in. We have not used the pigeonhole principle yet. So far, we have not used the pigeonhole principle. Otherwise, these integers are not divisible by M, and we place them in a box. Okay, so now I'm ready to create objects and boxes for the pigeonhole principle. These are going to be my objects. I've got M of them. And what I'm going to do now is I'm going to place them in the box that contains their remainder when I divide by M. In other words, modulo M. We can consider each of these numbers modulo M. I'm assuming that none of them are congruent to 0 in mod M. None of them are divisible by M. So I can place them in the box denoting their congruence classes. A little bit of number theory here, guys. Modulo M. But those boxes, those remainders in modulo M are just these values here between 1 and M minus 1. Why don't I have the congruence class of 0 listed here as a box? It's because I'm assuming that none of the original numbers were divisible by M to begin with. So when I take their remainder in mod M, right, that remainder cannot be 0. We're in this otherwise scenario over here. So what that tells me is that essentially the possible remainders are 1, 2, 3, and so on up to M minus 1. That's it. Can't have any other remainders here. So look how many boxes I have now. I have M minus 1 boxes, but I have M objects. The objects are these numbers right here. I'm going to put each of them into a box over there according to what its remainder is in mod M. And by the pigeonhole principle, here's the magic words, right? The pigeonhole principle now tells me that 2 of these boxes will have to be, one of these boxes must have at least 2 of these objects in it, right? That's the pigeonhole principle. So by the pigeonhole principle, there exists a box with at least 2 numbers from our list. Let me give this list a designation here. I'm going to star this list here, right? From our list in it. There has to be 2 of those. So what would those 2 numbers potentially be? Let's suppose that we have the following. In other words, two of the numbers in the list have the same remainder when I divide by m. So in other words, a1 plus a2 plus dot 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 plus ak, that's one of the numbers in my list. And then there might be another number in my list, a1 plus a2 plus up to al. And let's just fix the ideas here by assuming that k is less than l. I have two different expressions, two different objects from that original list that are in the same box. They're in the same box, and what that actually means is that they have the same remainder when I divide by m. So if they have the same remainder when I divide by m, in other words, they're in the same box here, maybe they both have a remainder of 2, then when I subtract them, wouldn't the result be divisible by m then? In other words, wouldn't m have to divide the difference of these? Let's write down the difference. Say the first one minus the second one. So if I take two things that both have the same remainder when I divide by m, then their difference is actually a multiple of m. But what is this difference? What is this difference? Well, I can see that there are a lot of common terms here, yeah? Canceling, and the k was less than l, so if I cancel up through the kth term, what's not canceled here? Well, it would be starting with ak plus 1 and continuing up through al. Isn't that exactly what I wanted to prove? That there are consecutive integers in my list whose sum is divisible by m. That's what we have. Let's just say which completes the proof. So we have to sort of do this problem with a couple of cases. We first have to just look at the original list and see if any of those are divisible by m. And if so, we're already done. Otherwise, we imagine that there's no numbers in the original list that are divisible by m, and that allows me to create not m boxes, but only m minus 1 boxes, right? That's the trick, right? Because I've got m numbers in my original list, and if I had m boxes, it wouldn't work. The pigeonhole principle doesn't work unless you have more objects than boxes. So we've actually reduced the number of boxes here. I only have m minus 1 boxes because I'm assuming over here in this case that I don't have any numbers that would be in the 0 box. So I've gotten rid of the remainder of 0 box. And so with one less box, now I can use the pigeonhole principle and I get two objects in the same box. Once I subtract those two objects, I create a multiple of m. And it consists of a sum of consecutive numbers from my original list. That's kind of how the idea actually works here. Okay. Hopefully this is making sense. Feel free to pause and digest a little bit. We've done a couple of slightly more abstract examples of the pigeonhole principle now. This one is very much a number theory oriented problem. And then of course we had to set up the boxes and the objects properly on this mail delivery problem from a little bit earlier. Both of these are really nice examples of the pigeonhole principle. Now, let me take just a moment to give you a couple of little rephrasings of the pigeonhole principle. These are kind of what you could think of as corollaries, I think, but I think they're worth writing down in our notes as well. Now that we've seen a few examples of it, so let me just call these, I'll call these corollaries of the pigeonhole principle. Still talking about the simple form of the pigeonhole principle. I haven't gotten into the strong form yet. Okay. So the first one is if n objects are placed into n boxes. Okay, so here we have to pause for a moment. Remember that the original pigeonhole principle requires us to have more objects than boxes. That's how we can then deduce that there's a box that has at least 2 objects in it. If I have n objects going into n boxes, it is possible that every box would have exactly 1 object in it. We cannot conclude here that there is a box with at least 2 objects in it. But what we can say here is the following. I need one more additional assumption. If n objects are placed into n boxes and no box has more than 1 object in it. So if no box has more than 1 object in it, okay, maybe before I fill this in, you can even think about what I'm going to say. Just using common sense here for a second. There's no box that has been duplicated. Doesn't that just mean then that since there are n boxes and n objects, that there'll be exactly 1 object in every box? Right? You can't have any box that's empty. If a box was empty, then there'd be some other box with 2 objects in it or more, right? So in this case, if there is no box with more than 1 object in it, then every box contains exactly 1 object. I'm not really going to prove this. This is basically common sense. But it's, of course, related to the pigeonhole principle, very much related to it. And the second point that I'm going to make here, guys, is basically the same thing again, except supposing that no box is empty to begin with. Right? So if n objects are placed into n boxes and no box is empty, then again, the same conclusion. If no box is empty, then every box, right? Then every box contains exactly 1 object. Every box contains exactly 1 object. Okay, so that's another pretty immediate conclusion that we can draw. So these are very natural, I guess you could say, conclusions from the pigeonhole principle. Let me do one last thing on this video and then we'll call it good. I just want to describe the pigeonhole principle in the context of functions a little bit. So this is a slightly more formal way of thinking about the pigeonhole principle from a very sort of mathematical point of view that doesn't involve like objects and boxes specifically. But let's suppose, so I'm just going to call this, let's just call this a formalization of the pigeonhole principle. Sort of a formalization of this. Namely, suppose that f is a function that goes from 2 sets x and y, where I want to assume that x and y are both finite sets here. Okay, so we don't have any infinite sets going on, we just have 2 finite sets. Then what we can do is we can say the following. If the size of x is bigger than the size of y, okay? So I want to draw a picture while I'm talking about this so we can think about it. I want you to think of X as containing all of the objects that we are looking at. So these are all just drawn right here, the objects. And then I want to think of the boxes or the pigeonholes as belonging in Y over here. Okay. And so as you can see, I have set this up in a situation where the number of objects is more than the number of boxes. And I would like to talk about creating a function now that goes from the objects to the boxes. You can literally just imagine assigning a certain object to a certain box as if it was an arrow of this function. So this object right here, maybe this is, some person. And here we're putting that person, we're mapping that person to their birthday, right? So we might have 365 boxes here. And maybe we have 366 people over here, right? More objects than boxes. Well, what you can see is that even if you try as hard as you can try, eventually, right? Eventually, two objects are going to get assigned. Whoops. These two objects, I guess, this one and this one, are eventually getting assigned to the same box. So it's just the Pigeonhole Principle kind of in the language of functions. And specifically what this means, if you remember from your study of functions, is that this just simply means that then F is not, in other words, it cannot be one-to-one. Such a function cannot be one-to-one. If the domain is larger than the codomain, then two objects are going to get sent into the same box. It's essentially the Pigeonhole Principle, if you want to think of it that way. Now, on the other hand, if the two sets are the same size, so this is a second point that we could also make here, right? Then if they're the same size, then it's, n objects and n boxes. It is possible for that function to be one-to-one, but F is going to be one-to-one if and only if that would be that there's exactly one object in each box. And that would actually also mean that F is onto. It would be literally if and only if F is onto here. Maybe to help us think about that, just suppose that we had, 4 objects in capital X and 4 elements in capital Y, right? Okay, the sets are the same size, right? Then, if the function is one-to-one, that means that two objects never go into the same box, right? So the function sends everybody to a different output. Well, if you send everybody to a different output, then you actually have to use all of the outputs exactly once. So every object has, or every box has exactly one object in it. Okay. So this is, again, just a functional formalization of a concept that is what we've been talking about throughout this video, which is the Pigeonhole Principle and some of its corollaries. I hope that you've enjoyed these examples. I hope that the way that the Pigeonhole Principle is being used has been fairly clear. It takes practice to figure out how to decide what the objects are, what the boxes should be, and how to use those objects and boxes together with the Pigeonhole Principle to prove something that might feel fairly abstract in the first place. It might not explicitly be shouting Pigeonhole Principle to you, right? So you have to be a little bit clever and a little bit experienced with practicing setting up the boxes and the objects in which we can then use this Pigeonhole Principle to help us. So the simple form of the Pigeonhole Principle just says, again, that if I have n+1 objects and I'm putting them into n boxes, that there's at least one box with at least 2 objects in it. Totally common sense, but it's worth reiterating one more time. In the next video, I'm going to talk about a little bit stronger form of the Pigeonhole Principle, and we'll take a look at some examples of that as well. For now, I will pause. I will let you think about what we've talked about today. Thank you so much for your time, for watching this video, And I look forward to seeing you guys all again very soon in the next video. Thank you.